Hello everyone, my name is Çağatay Yilmaz. Today, me and my colleagues, we are going to present the thermal feasibility of the new OCP HPCM module. Before I start, I would like to thank to the team, and I think this project represents a great representation of OCP spirit, because 3 different organizations came together to conduct this research. And today, we're going to be introducing the new OCP HPCM module, and I would like to point out it's really difficult to actually get a new product ready to the market. You have to design it, you have to prototype it, and you have to test it before you actually put it into the market. And designing the unit is actually the invisible side of the iceberg, so I would like to thank the OCP HPC sub-project group for this dedicated work. And today, hopefully, we're going to be answering one really simple question. How we would cool down a 1.4 kilowatt, a really small and modular HPC unit with only liquid cooling. So, for starters, I would like to invite Allan to the stage. He will be talking about the new design of this HPC unit.
Do I have to turn on? You've done it for me. These guys have done the thermal analysis of the HPC module, HPCM. So in the OCP HPC sub-project, we've been looking at trying to be able to look at a system-level perspective of making domain-specific computing architectures, being able to build them really easily and quickly for heterogeneous implementations in different interconnect topologies, etc., but very easy from a research and development perspective. And so this is the fundamental building block where you can mix and match really powerful processors and accelerators with the media, the different types of memory and storage media, and get its low power footprint by using 3D-izing the actual system aspects, as well as all the 3D silicon that you were hearing about like today. And so that's what this module's about. This talk isn't about this module, but we have a poster session out in the hallway there, and I'll be standing by that poster. So if you'd like to learn a little bit more about this module, I'll be more than happy to walk you through it.
Thank you, Allan. So I'm leaving the stage to Ender to explain the thermal studies.
Okay. Hi, everyone. I'm Ender Demirel. My background is on the development of open source CFD models for the simulation of different problems. So in this work, we first developed an open source computational model for the thermal analysis of HPCM. And second, using this proposed numerical model, we developed a liquid-cooled system. But we should keep in mind that this study is an ongoing research study. So we have developed our numerical model, and we will be able to use this numerical model for the optimization of the thermal distribution. So 3 regions are available for this configuration: the air region, solid region, and liquid region. So the numerical model should consider thermal effects and thermal distribution in each region. So we have developed a conjugate heat transfer numerical model in which governing equations are solved in each region. There are a bunch of equations here, but I don't want to give the details of the mathematical model. If you have some questions, we will be on the poster, so we can discuss the details. So the flow enters to the flow domain, the air enters to the flow domain here, and emerges from the domain at this section. And the heat source is located at the top of the cold plate, and the thermal paste is applied in order to increase the heat transfer between heat source and the cold plate. So the flow rate is in the range of 0.3 liter per minute and 4 liter per minute. So we want to benefit from the waste heat in this project. So the outlet or exhaust temperature is required about greater than 25 degrees Celsius for this domain. So the conjugate heat transfer numerical model couples the fluid-solid interface using these expressions, and governing equations are numerically solved in these regions. The effect of thermal paste is important in the numerical model, so we should consider these effects. And there are two parameters in here: the thermal conductivity of the thermal paste and the thickness of the thermal paste. There are two reasons using this thermal paste: to eliminate the air gap between the heat source and the cold plate, and to increase the heat transfer. So we developed a numerical approach here in order to simulate the temperature jump between the CPU and the cold plate in here. So the numerical model has been developed based on open form libraries, which is an open source CFD framework. The finite volume method is used for the numerical solution of the governing equations. An overlapping multi-region mesh is created using Salome. The mesh should not be overlapped in this approach. So this is a great flexibility for us to model different regions for a consistent numerical mesh in here. So when we develop our numerical model, we focused on the development of a microchannel heat exchanger to distribute the heat on the cold plate. There are different alternatives in the literature to distribute the heat on the cold plate technology. This is our first attempt here. So the flow enters to the flow domain here, and the liquid is traveled to the outlet section, and the heat is transferred to the outlet of the system in here. So our numerical model shows the temperature distribution inside the domain. So the maximum temperature on the CPU is predicted about 100 degrees Celsius, but it is possible to reduce this temperature using different flow rates or using different inlet temperatures for the liquid. The maximum temperature is observed on the heat exchanger is about 86 degrees Celsius, and the water is about 84 degrees Celsius. And the flow uniformity is a very important and a significant parameter for the assessment of the efficiency of the cooling system. So the flow uniformity through the microchannel is observed in this graph. So we are trying to obtain a uniform flow inside this microchannel design. So as I said before, we will try different microchannel designs in order to increase flow uniformity for this numerical model, because we observed some recirculation regions which will reduce the cooling efficiency of the system. So the numerical model also reveals the thermal transition between regions, because there are different regions, solid, air, and liquid regions. So the thermal distribution between those regions can be observed from this numerical approach.
Actually, we are also getting this product ready for commercialization. So we are trying to standardize the water regimes required for such a module, because besides the IT unit, we have to make a specified cooling unit ready for the market. So in this case, when we finalize this project, the water regimes and the general user manual can be also open to the market.
Thanks, Çağatay. Here are our results. An HPC module designed by Allan is introduced in this study. So an open source numerical model has been developed based on open form libraries for the analysis, for the thermal analysis of the system. The thermal distribution over solid and liquid regions can be observed from the numerical model developed in this project. And the resistance effects of the thermal paste applied between the heat source and the cold plate can be considered in this numerical model. Different thermal paste features can be investigated based on the numerical model. So a microchannel design is implemented to the HPCM for the liquid cooling of the system. So here are our feature studies. The different microchannel designs are available in the literature, so we can implement these microchannel designs and assess the cooling efficiency of the system depending on the numerical results. Different inlet configurations can be investigated to optimize the internal parameters of the cooling system. Thermal features of the material of the HPCM will be investigated in the future. So optimal inlet water temperature and flow rate should be determined in order to increase cooling efficiency of the system. Thank you for your attention and time. If you have some questions, we can answer your questions.
I don't know if we have any time to accept any questions, but please.
Okay, real quick one. So you have a water cooling system and an air cooling system. What are the relative heat fluxes to these two different directions? That is, do you actually need the air?
Okay, actually in this particular unit, we try to avoid usage of air cooling. We want to cool down whole the unit with only water and with conduction. We don't rely on air cooling.
Is that what the heat fluxes do? You get very little heat flux to the air.
And we found that most of the heat flux is exhausted with the water. About 95% of the heat flux is transferred to the region.
Okay, thank you.
Thank you for your
Thank you
attention.
so much.